So let's look at, again, some of the interactions. Ion-dipole interactions are what make ionic solids dissolve. We talked a lot, about sort of empirically what happens when you dissolve ionic solids, that there's this tug of war between the ion-ion interactions, which are quite strong, and then the ion-water interactions, which are less strong. But as you can see, each ion gets to form lots of ion-water interactions. So the sheer number of ion-dipole interactions formed between water and ions is sometimes, in the cases of soluble molecules, enough to overcome the very strong Coulombic interactions. So that's what, this is the situation. It's just the tug of war. If the solute, so if the dipole ion interactions are strong enough, it dissolves. If they're not strong enough, it doesn't dissolve. If you recall back, you remember, oh yeah, there were a lot of +2, -2 solids that tended to be insoluble. In that case, the Coulombic interaction is 4 times as strong, and maybe the ion dipole forces are only about 2 times as strong. Because yeah, you have twice as large a Coulombic interaction, but why not go with a 4 times stronger interaction? So those are the sorts of patterns you see there. Yeah, so when some terminology, when ions dissolve in water, we call them hydrated ions. Each ion is surrounded by water molecules. And the formation of these ion-dipole interactions cause the heat of hydration, the process of going from gas phase ions to ions in water, is extremely exothermic because you get the creation of lots of ion-dipole interactions. These hydrated ions are actually quite interesting. The water tends to stick to them fairly strongly. And so if you're doing any sort of water filtration, you need sort of channels large enough for hydrated ions to go through, because the ions might not go through on their own. The ion behaves as if it's much bigger, because it's essentially carrying around these waters almost permanently. I mean, it's not permanent. It's not as strong as a covalent, an atomic bond or covalent bond or even ionic bond, but it's they're still fairly long-lived, and so it has its little entourage that it carries around because it's it's electrostatically important. Okay, so heats of hydration. So for aqueous solutions of ionic compounds, the energy added to overcome the attraction between the water molecules and added together with the energy released in forming attractions between the water molecules and the ions is the heat of hydration. So it's the breaking the water-water bonds, breaking the solute-solvent interactions, and gaining the ion-water interactions. That's the heat of hydration. The attractive force between ions we've seen before, that's the lattice energy. And so the change in enthalpy of the solute-solute interactions, that's literally just minus the lattice energy that we've seen before. The attractive forces in the water, you have to break the H bonds. The attractive forces be the ion in water or ion dipole, which are stronger than H bonds. So the enthalpy of hydration is the heat released when 1 mole of gaseous ions dissolves in water. And that would be the heat of the solvent interaction breaking and the gain of enthalpy from the mixing. So what we would generally see is, if we're looking at the heat of solution, you have the lattice energy, which is the enthalpy of breaking the solute interactions. That gets you to the gaseous state, gaseous ions, and then the heat of hydration is bringing in those gaseous ions to be hydrated, also very large. In the case of potassium fluoride, you can see they just about balance each other out. So comparing the heat of solution to heat of hydration, because the lattice energy is always exothermic, you always get a large amount of energy released. The size and sign on the H solution tells us something about the H hydration, right? Because those two parts, the H hydration, which is the solvent of water plus the solvent-solute interactions, that is the heat of solution is just the sum of that and the lattice energy. So if we know the lattice energy, we know the heat of hydration. So if the heat of solution is large and exothermic, the amount of energy it costs to separate the ions is less than the energy released from hydrating the ions. So if change in enthalpy on hydration is greater than the change in enthalpy on breaking the solute, i.e. the lattice energy, then it's exothermic. We gain more energy by hydrating. If the heat of solution is large and endothermic, then the amount of energy it costs to separate the ions is more than we gain back by hydrating the ions. So if delta H hydration is less than delta H solute, then the delta H of solution is endothermic. We don't gain quite enough energy by hydrating the ions. And of course, when the hydration is approximately equal to the heat of breaking the solute-solute interactions, then the delta H of solution is 0, which means they will be soluble because entropy will be driving that.